Hello everyone, I'm Manu at Kiln, and today we'll talk a little bit about the roadmap of Ethereum after Shapella. And Vitalik wrote a roadmap with different parts like the merge, the Scourge, the purge, the surge, the verge, and the splurge. And we'll talk a little bit about these topics today. And just before talking about the future of Ethereum, let's talk about the past. 10 months ago, somewhere between the National Teddy Bear Day and the October 1st start, we had the end of proof of work. So transition from mining to staking. To me, it seems it's like 10 years ago, and it was only 10 months ago because things are moving very fast. And 3 months ago, in April, we have the Shapella upgrade, which allowed the staker to withdraw their 32 ETH and the rewards I earn on the consensus layer. And yes, it was only 3 months ago, and it seems like to be a very long time ago. And yes, I guess you don't worry if you cannot read. I will explain it more in details after. This is the roadmap proposed by Vitalik a few months ago, introducing the merge, the surge, and so on. Very often, when people see this roadmap, they think that it's a very linear stuff, like first the merge, and after the surge, and after the scourge. But actually, it's not the case. The Ethereum core dev and the Ethereum researcher are working on all of these topics more or less in parallel. And yes. So let's go for the merge. We have to distinguish two stuff, which are the merge event, merge event was on September, and the merge part, which regroup a lot of features. So basically what we had a few months ago, the life was really exciting. We had a lot of GPUs, a lot of heater, a lot of fan, a lot of energy consumption. And sometimes we had blocks every 2 seconds. Sometimes we had blocks every 30 seconds. It was very exciting. And, and now with the merge, no more excitement. It's very boring. 1 block every 12 seconds exactly, and no more electricity consumption, and we know in advance who is going to propose a block. Less exciting, but well, at least it's better for the network. And yes, and also now staker can withdraw. So the first staker had to stake 32 ETH, and they didn't know when they will be able to retrieve it, and now they can. So it's done. So let's talk about the future. Distributed validator, or DVT, for distributed validator technology. What is it? When you run a validator, you need 2 keys, a public key and a private key. And you need to keep the private key hot because exactly once per epoch, an epoch lasts approximately 6 minutes. Once per epoch, you have to sign an attestation, and you have to sign this attestation with your private key. So you need to keep this private key hot. The issue is, if your private key gets compromised, an attacker can store your private key and can attest on your behalf, and so you can be slashed. And basically, when you are slashed, you lost at least 1 ETH, which is the bad stuff. And so there is a new technology which is called DVT, for distributed validator technology. And actually, you can split your validator key into multiple shares. And for example, you can split it on 5 shares. And you can say, OK, I split those 5 shares on different nodes. And if, let's say, 3 nodes out of 5 nodes agree on an attestation, then you merge this attestation on the shares, and it gets a real attestation on the network. And I like to think DVT about Voldemort Horcruxes in Harry Potter. You know, Voldemort just splits his sword in 7 Horcruxes. You can kill 1 Horcrux without killing Voldemort, and it's the same. You can stall 1 share without killing the whole validator. This is DVT, a very interesting technology. Other one point is secret ledger redaction. What is this? Currently, everybody in the world knows approximately 30 minutes in advance who is going to propose a block. And because it's a known stuff. And the issue is, if somebody in the world is able to map the public key and IP address, for example. So an attacker will be able to DDoS, will be able to prevent the proposer to propose its block. And if an attacker does that for several blocks in a row, we will have a loss of finality, and eventually the Ethereum beacon chain will get in a lot of troubles. And in order to avoid that, we have secret leader detection, which is a feature which allows only the proposer to know that he will going to propose a block, and that's all. Nobody else knows that a given validator will propose a block. It adds some security feature to the blockchain. And yes, there is also another very interesting talk of a feature about increase of max effective balance. I won't talk a lot about it right now because there is Mike Nutter somewhere here from Ethereum Foundation, who will talk about it at 2:30 p.m. Very interesting feature too. And finally, all this stuff, we want to go to single slot finality. Now, what is finality in the blockchain? For example, when you make a transaction, you are at a party and you want to buy a beer at a party. So you make the transaction for your beer to the bartender, and the bartender gives the beer. Unfortunately, there is no guarantee that your transaction won't be reverted before up to 30 minutes. Ideally, you should wait for 30 minutes before drinking your beer, and so your beer will be hot and without any gas inside. It's not interesting. And this nice feature, single slot finality, the purpose of it is to ensure that every transaction in every block will be finalized. By finalized, I mean you cannot revert it within a single slot, so within 12 seconds. And yes, it will be really close to like we have today with MasterCard or Visa. When you pay something, you don't need to wait 30 minutes, to be sure the transaction is okay. This is for final slot finality. And yes, and the last one for merge is quantum safe aggregation signatures. Today, the beacon chain heavily relies on BLS technology, BLS cryptography. BLS cryptography relies on elliptic curves, and elliptic curves are not safe for quantum cryptography attack. And so if you want to be sure that when quantum computing will be very well known, if you want to be sure that the beacon chain will stay up, we have to find a new way to aggregate signature without this elliptic curve, or at least we need to change a little bit the cryptography algorithm behind it. That's for the merge. Okay, this one is very interesting. I guess everybody heard about EIP for 844, but maybe not everybody knows exactly what it is. Just very quickly, today the Ethereum network, which we can call it L1 for layer 1 Ethereum network, can handle up to, let's say, a few dozen of transactions per second. And even if you do that, even if you fill your block, the price of the gas will go up exponentially, which is something we don't want to get. That's why there is some other technology like optimism, like zero-knowledge rollup, which implements something we call rollup. So you have a lot of transaction, you make a rollup with it, and this rollup is only one transaction of the L1 Ethereum. And in order to do that, the rollup needs to post some data on the L1 Ethereum, and this data, actually, the rollup doesn't need this data to be available for the eternity. They just need this data to be available to a few hours, or maybe days, or maybe weeks, maybe months maximum. And there is no way, actually, on Ethereum to post data with a limited amount of time. And so that means that every data will be here on all of the network nodes for all the eternity, which is a waste of resources. And, oh, what's happening? And it's okay. And so EIP for IFR4, which is also named proto-dunk sharding, introduced a new type of transaction which can handle something which is called blob data. Blob data is just a kind of data, any data we want, which will live not on the execution layer, but it will live on the beacon chain with a limited amount of time. And this limited amount of time will allow to really lower the cost of transaction on L2 by some order of magnitudes. And it's what EIP for 844, also named proton sharding, introduced. A very cool feature, really cool feature. And just after, so we have, in order to have this EIP for 844, we need DA sampling. DA samplings means data availability samplings. Why we don't need that? Because so we said that the beacon nodes will handle some data, and we have to be sure that this data is available. And we have to be sure this data is available without retrieving all the data all the time, because it's too costly. And so there is a technique called data availability sampling, where we just need to retrieve some few kilobytes of data on some nodes. And if, for example, we retrieve 50% of the whole data, we have the statistical guarantee that more than 99.99% of the data is really available. How is it possible? We use something called Reed-Solomon code. Actually, everybody uses this Reed-Solomon code every day without knowing it. It's in flash codes or QR code. So you have the QR code from Kiln to a GitHub repo. You can scan it. But if you scan this one, which is exactly the same, but with some coffee split on it, it will work. Why does it work? Because there is a data redundancy inside the QR code, and the same technique will be used for data availability sampling. So it's okay if some nodes lose the data. We don't care, because actually we are statistical guarantees that the whole data will be available thanks to the Reed-Solomon code. Very interesting feature too. And yes, so let's go to the Scourge. Currently, I guess you know what is MEV. And so right now, when a validator wants to propose a block, he doesn't build the block itself. It was the case before. Before, the miner builds the blocks themselves, and even the validator at the beginning of the beacon chain. And now there is two different roles. There is a block proposer and there is a block builder. Block builder is actually totally external entities, and block builders send all their blocks to something which is called a relayer. There is a lot of relayers. There is blocks root, there is block native, there is flashbot, there is ultrasound money. And the big issue with this system is builder has to trust the relayer and block proposer has to trust the relayer. So the whole blockchain, Ethereum blockchain, is trustless, but there is the relayers, which are not so many, and everybody, builders and proposer, have to trust it. This is what we have currently with something which is called flashbot auctions, or also sometimes we call it MEV boost. And we should really move from it by integrating the proposer block separation directly in protocol. And again, I won't talk too much about it because at 4 p.m. we have a panel with Justin Drake from EF, with Yuri from Bloxroot, and with Stefan Gosselin from Frontier, and previously from Flashbot, which will talk about it. And also we'll talk about MEV burn. It's basically it's like EIP 1559 when you burn the base fee, but with MEV burn you will burn the MEV. So we like to burn a lot of stuff. This MEV burn. And yes, and finally there is Verge. Oh, this one is really also very interesting. Currently, Ethereum network is really inefficient. When a user wants to send a transaction on the network, so the user sends the transaction, and all the nodes of the network has to replace the transaction. And it's really a waste of resources because everybody has to recompute exactly the same thing. And this is currently needed for the trust of the system. But it is very inefficient. Everybody computes. And there is a technology called SNARK for succinct non-interactive argument of knowledge, which is totally a change of paradigm, where in this case, you have a few people, or even only one node who computes all the transactions, And this node, which is called the sequencer, actually computes the transaction and generate a proof. Generating a zero-knowledge proof is very, very complicated. It requires a lot of CPU, a lot of memory. But you need to do this only once. And so basically, there is one sequencer. I'm not sure the term sequencer will be used in the SNARK for L1. Actually, the word sequencer is used in L2. And this one sequencer will run, and all other validators, all other nodes in the network won't run the transaction, but will only verify the transaction. And generating a proof is very costly in terms of CPU and RAM, but verifying a transaction is very cheap. So we'll move from everybody computes to a few people, or maybe one, will compute, and everybody will verify. And this will really allow to increase a lot the amount of transactions per second the Ethereum network can run. And finally, it will enable the increased L1 gas limits. Currently, each block has only 30 million gas maximum, which limits the number of transactions you can run per second on the network. And if we are able to enable the SNARKs for L1 EVM, we will be able to really increase very big factor the number of gas limits per block. And it will be really a game changer for the Ethereum network. And yes, that's pretty all. And, if you have any questions, there is 3 minutes.
Yeah, I'm just curious, like, for the fully snarked Ethereum, like, if proof generation is complicated, wouldn't that kind of reduce the decentralization of the network because the nodes have to be much more like powerful, higher compute?
Yeah, I see what you mean. Actually, the network will be still decentralized because everybody will have to verify the proof. And we need only one sequencer to generate the proof. But it doesn't mean that we will have only one. I mean, the technology says we need at least one. But if you want to run it, you can. And you can publish a block. Yeah.
How would you decide which one is computing the transaction?
I'm not sure totally about it right now. I don't want to say any bullshit. This one is really, very far away. I guess we won't see it before, if I say 5 years, I guess I'm very optimistic. And maybe, let's say, 10 years. A lot of stuff can change. Yeah.
What would be the technical requirements to run such a sequencer?
Right now, if we are based on what, for example, Starkware does, I don't remember exactly, but it's a really huge computer with something like at least 32 CPU and a few gigabytes of RAMs, a few dozen of gigabytes of RAMs. But I guess this requirement will be much lower in the future because proof generation will be more efficient than today. But I cannot guarantee.
Okay, thanks, guys.
That's all. Thank you. Thank you very much.